Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today's one of my favorite topics. I don't think it was when I first learned these problems way back in the day, but I've come to like them just because you do a lot of real-world examples, and it really just shows you how calculus is applicable to a lot of real-world scenarios. So these are called related rates problems. We're going to take a look at an introduction problem. I'm going to give you guys time to kind of play around with it and think about how you would solve it. And you may not get all the way there, but you may be able to come up with some useful equation that we'll then reference later. But essentially, we have an airplane flying at a height of 6 miles up in the air. The airplane is S miles from the radar station. So that's the direct distance is what S is representing. And the station, the distance between the plane and the station is decreasing at a rate of 400 miles per hour when the plane is 10 miles from the station. So when S equals 10, that distance is decreasing by 400 miles per hour. We need to figure out what's the speed of the plane at that time. So when S is equal to 10, we need to figure out the speed of the plane. So again, just take a couple minutes, think about it. Is there any equation you can come up with based off of the diagram? I don't expect you to get all the way to the end and finding that speed, but see what you could set up, and then we'll see if that anything that you came up with was useful later on. Okay, so one of the first things I think I would notice is that we seem to have a right triangle here. We don't seem to have one. We certainly do. And if I think back to geometry, or I guess you've certainly talked about in other courses, but maybe geometry you've harped on it the most. I'm going to invoke the Pythagorean theorem, right? So the sum of my legs, the sum of the squares of my legs, so x squared plus 6 squared is equal to s squared, would be how we invoke the Pythagorean theorem here. I can also make that x squared plus 36 is equal to s squared. Now, we're being asked to find a speed. We're trying to find the speed of a plane, and neither of the variables in our equation represent speed, right? One represents the horizontal distance between the plane and the station, and one represents the direct distance, or that we could think about the net distance. So we're going to have to either do something to this equation or come up with a different one. Now, they do give us another useful piece of information, right? It says the distance between the plane and the station is decreasing at a rate of 400 miles per hour and the plane is 10 miles from the station. So they're basically telling us how this distance right here is changing, right? And maybe that sets off a bell in our heads, right? If we're thinking about how a function changes, well, we may be thinking derivative, right? The slope of the tangent line for a function tells us how that function is changing at that certain point or at that instant in time. So maybe let's just see what happens if we take the derivative here. Now, we see two variables. We see an x and an s. And we have to think, are x and s's, do they represent constants? Is one of them what we need to take the derivative with respect to? Or is there some other variable that x and s are really functions of? So we have to think, what makes x change, right? Why does the horizontal distance change or increase? Or what makes it change? Well, it's the time, right? At a certain time, the horizontal distance between the plane and the station may be larger or it may be smaller, right? Maybe the more time that goes on, the plane gets closer and closer to the station, right? Same with direct distance. As time increases, that distance, right, as the plane moves this way, oops, it was my eraser, but as the plane moves this way, the distance between itself and the station is going to be less than what it was when the plane was over here. Right, so s and x are really functions of time. We could think of that as, s of t and x of t, because they're both functions of time. So we're going to take the derivative with respect to t. So derivative with respect to t, or time, because these distances are changing with respect to time. As time increases or as we go backwards in time, those distances increase or decrease. So we have to apply a chain rule for both x and s. Remember when we did implicit differentiation, we only had to invoke the chain rule for y because y was the function of x. Well, this time x and s are both functions of t. So here we go. Buckle in. Take the derivative of the outside, so 2x, times the derivative of the inside function, so dx dt. Plus 0, because derivative of a constant with respect to any letter is going to be 0, is equal to 2s ds, derivative of s with respect to t. Now you'll notice, well, we've got a lot of different unknowns. We've got an x, we've got an s, we've got a dx dt, we've got a ds dt. Let's think about which one of those we need to solve for. We need to think, what is the speed of the plane? Well, we know that x and s are distances, so they're not speeds, right? And we know that ds dt is how quickly the distance between the plane and the station is changing. But that's not going to be the speed of the plane, right? The plane is moving horizontally. So the change in horizontal distance is going to represent the speed of the plane. So we are going to be solving for dx dt. So we better be able to figure out all those other unknowns, x, s, and ds dt. Well, let's see if we can do it. Do we have an s value? We sure do. We have s is equal to 10 because that is the distance at which we're trying to find the plane's velocity when s is equal to 10. So I've got 2 times 10. I also know that ds dt is essentially negative 400 miles per hour, just negative 400. I know it's negative because it says the distance is decreasing, right? So if a function is decreasing, the position function or the distance function is decreasing, the derivative is going to be negative. So negative 400 here. All right, let's move on to the other side. I don't need to know what my dx dt is because I'm going to go ahead and find that. That's what I'm going to solve for. And I don't need to change my 2, obviously. I just need to figure out what x is. Well, is there a way, if I know that s is equal to 10, can I figure out what x is when s is equal to 10? Sure can. I'm going to use my original Pythagorean theorem equation. So I'm going to get x squared plus 36 is equal to 10 squared. I get x squared is equal to 100 minus 36. I get x squared is equal to 64. I get x is equal to plus or minus 8. However, we don't need the negative value, right, because we're talking about a distance. So we're just left with positive 8. So x is equal to 8. And now we just need to go ahead and simplify and solve for dx dt. Let's come over here. So I get 16 dx dt is equal to 20 times negative 400, which is going to give me negative 8,000. Divide both sides by 16, I get dx dt is equal to negative 8,000 divided by 16. This is going to give me negative 500. And we have to remember that we're talking about a speed. So speed is the absolute value of velocity, which is what dx dt is. So speed is equal to the absolute value of dx dt, which is equal to the absolute value of negative 500, which is equal to positive 500 miles per hour. So the speed of the plane is 500 miles per hour. Now, that seemed like a lot of work, and it was, and It may not have been clear which direction to take at certain times during the problem. But some things you can garner from this that'll hold true for all of our related rates problems is that when we take the derivative, we're going to be taking the derivative with respect to t, or with respect to time. So whatever variables we have that we're taking the derivative to, those variables are changing with respect to time, so we're taking the derivative with respect to time. Let's walk through another one, and I'm going to talk about the important things that we need to be on the lookout for when we're trying to solve a related rates problem like this. So let me clear this work. All right, so let's look at the problem on page 2. And again, just what we mentioned above, a related rates problem involves two or more variables that are both changing with respect to time, which means, again, when you take your derivative, it's going to be a derivative with respect to time, or d over dt. All right, here's the problem. Air is leaking out of an inflated balloon at a rate of 230 pi cubic centimeters per minute. The balloon is in the shape of a sphere. At the instant at which the radius is 4 centimeters, what is the rate at which the radius is decreasing? So I'm going to start with just sketching a picture. Maybe that helps. It does say it's a spherical balloon. Maybe that'll make it look a little bit more spherical in shape. And let's think about the variables that it mentions. And you can also, again, put the rates in here as well. So it says air is leaking out of the balloon at a rate of 230 pi centimeters cubed per minute. So that is going to be one of the pieces of our equation, the derivative of the volume with respect to time, or the rate that the volume is changing with respect to time, right? If air is leaking out, the volume is changing. So in this case, the rate at which the volume is changing, we just say dV dt. It also mentions a radius, right? It says at the instant at which the radius is 4 centimeters, that is when we need to figure out how the radius is decreasing, or the rate at which the radius is decreasing. Well, there's another one. The rate at which the radius is changing is going to be dr dt. So those are the three things that the problem references. One of these is defined with a constant value. That is dV dt. Right? It says dV dt, and in this case it's actually going to be negative because air is leaking out. So the volume is decreasing if air is leaking out, which means the derivative is going to be negative 230 pi. Question 3, I kind of do that in step number 1 as well. When I'm looking at the variables, I also think about the rates. So we're told that dV dt is negative 230 pi. The thing that we need to find is dr dt. So dr dt is what's in question. And again, I'm not concerned that you have these in the exact boxes that I do. I'm concerned that you're thinking about these questions. So you're thinking about, okay, what are the variables that are listed? What are the variables that are in the picture, the diagram? What are the rates that could be present? Sometimes the rates are mentioned. Sometimes they're not specifically mentioned. Generally they are, though. I think in our first problem, they were mentioned, they just weren't specifically put on the diagram, right? We had to figure out that we had to come up with a dx dt and a ds dt. They weren't explicitly given. Same thing here. We have to understand that the rate at which air is leaking out is dV dt. It's a change in the volume. And the rate at which the radius is changing is going to be dr dt. So we have these three things. We have two rates and a variable. And we need to figure out how can we all relate those. So how can we relate essentially volume with radius when we're talking about a balloon that's a sphere? Well, if we think back to geometry or middle school, actually, maybe it was the first time that we saw this, but the volume of a sphere is equal to 4/3 pi r cubed. A lot of times they will give you the volume formula or the surface area formula or some other formula that you may need if it's one that you're not using all the time, right? So the Pythagorean theorem they're not going to give you, but if it's one of those volume equations like the volume of a cylinder or the volume of a cone or maybe the volume of a sphere, they're probably going to give you the formula because they don't want that to be the thing that holds you up from solving for the unknown, right? They don't want a non-calculus thing to stop you from understanding how to set up and solve the problem. So they normally would give you this equation. I know they didn't in this problem, but know that they probably will. It doesn't mean it's, you shouldn't have this memorized, or you shouldn't understand the volume of a sphere equation, but they may give it to you depending on whether they think it's obscure or not. Okay. We know that now we need to differentiate this, because if we differentiate it, then we will get some dv dt and dr dt unknowns. So I'm going to do this over here. Volume equals 4/3 pi r cubed. Let's fix that a little bit. Going to differentiate both sides with respect to time. So d dt the left-hand side, well, that's easy. I just get dv dt. The right-hand side, I've got to apply the power rule first. So I get 3 times 4/3, which is going to give me 4 pi r squared, times the derivative of r with respect to t. So times dr dt. Now I just need to substitute in. I know what dv dt is. That's negative 230 pi. I know that my r is equal to 4, right? Because that's the value of r when we need to figure out what dr dt is. Now I can see that I have a pi on each side as a factor, so I can simplify. And I can simplify my 4 times 4 squared. So negative 230 equals 4 times 16, which is 64 dr dt. And we're just going to divide both sides by 64. So negative 230 divided by 64 is equal to dr dt. And I can divide both my numerator and denominator by 2 to get negative 115 over 32. This is my dr dt. And my units, well, I'm talking about a radius, which is one-dimensional, so it's just going to be centimeters, per, what's our rate of time? Minutes. So that would be our dr dt. Again, you're going to get used to asking yourselves these different types of questions, and then trying to understand what equation to come up with based on the variables that you have and the rates that you need defined. We're going to do one more problem. So let me clear this. We are just going to probably do the next one, I think, but let me check. Let's see which one I want to do. We're actually going to do this next one. It's different enough from the first two where I think you'll benefit from seeing on the video. So it says a television camera at ground level is filming the liftoff of a rocket that is rising vertically according to the position equation S equals 50t squared, where S is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. So we're looking at that horizontal distance is 2,000 feet. We need to find the rate of change in the angle of elevation of the camera 10 seconds after the liftoff, right? So the camera is following the rocket. So the angle that the camera has with the ground starts off with 0, right? Because it's probably just looking straight ahead. As the rocket rises, the camera starts to tilt upwards. You could just think of it as your eyes watching the rocket. You'd be looking straight ahead when the rocket's on the ground. As the rocket lifts off, your head is going to tilt backwards, and you're going to be looking higher and higher into the sky, which means the angle that your eyesight is making with the ground is going to increase. And that's this angle right here, this theta that they're talking about. Okay, we need to find the change or the rate of change in the angle of elevation 10 seconds after liftoff. So let's ask ourselves some questions. What are some of the variables we see here? Right? Well, we see a theta. Okay. We see an S, right? This S is the vertical height that the rocket is off the ground. It also mentions the rate of change in the angle of elevation. So d theta dt. It also gives us an equation for S, right? It says that S is equal to 50 t squared. And we know that S is a function of t, but now it gives us the specific function. And although 2000 is not a constant, it is a constant, it's not a variable, it is something to pay attention to. So we can say, are any of the variables above variables defined with a constant value? If so, list them and their values. Well, the horizontal distance is, that's equal to 2000. So if you wanted to, you could say horizontal distance equals 2000. I know we didn't list it as a variable above, but it is something that's going to come into play. Okay, we need to figure out what are the rates that we are given and the rates that we need to find. Well, we're not given any rates specifically here, right? We're not given the rate of the rocket's velocity as it moves forward, and the only other rate is the d theta dt. So d theta dt is the one that we are trying to find, and there is another rate, ds dt, which we could find. It doesn't tell us, but if we took the derivative of s, right, we could figure out what ds dt is. That's going to be 100 t. And you don't have to do this at this step. You'd figure out how to do it at the next step. I'm just doing it here because we're being asked the question. Number 4 says, write an equation that relates all the variables together. Well, how can I relate theta with s and the constant 2000? Well, it's a right triangle, and if I'm talking about an angle, I'm going to use some trigonometry. This is the opposite side compared to theta, and this is the adjacent side compared to theta. So I am going to be using tangent. So tangent of theta is equal to s over 2000, which is really equal to tangent of theta, or let me just rewrite the whole thing to make it a little bit easier to follow. Tangent of theta is equal to 50t squared all over 2000. So this is the equation I'm going to be working with. It will allow me to get a d theta dt, which is what I need to solve for. Okay, let's go ahead and take the derivative. I'm going to do this up here on the left. I've got tan of theta is equal to, and actually instead of writing 50 over 2000, I'm just going to simplify that to 1 over 40, right, if I make it a fraction. Or you could just make it 0.025. That also works. I'm going to use 1 over 40 though. 1 over 40 t squared. It'll just be easier when we use the power rule. And I need to take the derivative with respect to time. And of course, I'd encourage you to pause the video and be working through this on your own before you see how it's done, because I think you have enough knowledge to solve this. It just, you need to take the derivative of tangent rather than some other function. Okay, derivative of tangent is secant squared. So that's the derivative of the outside function, derivative of tangent. Derivative of the inside function with respect to time is just going to be d theta dt. Okay, so secant squared of theta times d theta dt. That is equal to 1 over 20 t. And because t is what I'm taking the derivative with respect to, there is no chain rule here. Okay, let's see. Do I have enough things to substitute in to just leave the d theta dt by itself? Well, I have a t value because I know I'm looking for d theta dt 10 seconds after liftoff. So let's go ahead and substitute that in. Secant squared of theta times d theta dt is equal to 1 over 20 times 10. So I get secant squared of theta d theta dt is equal to 1 over, not 1 over 5, 1 over 2. 1 over 2 or 1/2. Well, the problem here is I still need to know what my angle is. What's the angle 10 seconds after liftoff? Because right now I have two variables. I need to know what my theta is so that I can solve for d theta dt. Well, let's go back. Is there any way for me to figure out what theta is? Well, I could go back to my original equation if I want, right? And I could substitute in 10 for t and then solve for theta. So let's go ahead and do that. You need a lot of space when you're doing these related rates problems. So I get, oops, it's my eraser still. So I get tan of theta is equal to 50 times 100, 10 squared, all over 2,000. So I get tan of theta is equal to 5,000 divided by 2,000. I get tan of theta is equal to 5/2. And now I still got to solve for theta. What you can do is use inverse trig. So I get theta is equal to inverse tangent of 5 over 2. And I'm going to round to 5 decimal places because at the end I want to round to 3. So I want to go to something more if I'm going to do it in the middle of my problem. And this gives me approximately 1.19029. So that's the value I'm going to take for theta. I'm going to bring that over here. So I get, and I can actually rewrite secant squared, right, as 1 over cosine squared of 1.19029 times d theta dt equals 1/2. And then I can multiply both sides by cosine squared of 1.19029. And that's going to give me d theta dt. I'm going to simplify cosine squared of that number. Which gives me 0.13793, which is approximately 0.069 radians. I'm talking about how that angle changes, radians per second. You could use degrees, but most of the time, well, in calculus, we're assuming radians unless we're specifically told. So you could give an answer in degrees. Your units would just be different, and you need to make sure your calculator was in degrees when you were performing the work. But unless told differently, perform your calculations in radians. That's what's expected when you're doing a calculus problem. All right, that's going to wrap it up for this video. I think these 3 examples give you some stuff to look back on as you work on future problems. As always, enjoy the rest of your day, and I look forward to seeing you next time.